Welcome to VFD Vibes, your place for all things related to variable frequency drives. If you're interested in how to make things turn, or manufacturing technology in general, then this is the place for you. I'm your host, Greg Wichman, and today we're tackling a topic that's both technical and crucial, short circuit protection. Of course, being Yaskawa, also how it applies to variable frequency drives. Short circuit protection isn't just about ticking off a compliance box. It's about protecting people, equipment, and operations from serious hazards. From arc flash events to equipment failure, overlooking available fault current can have dangerous consequences. Joining me is Steve Brohl, Chief Product Line Manager for Low Voltage Drives at Yaskawa America. Steve's going to help us unpack what you need to know about SCCR, UL testing, and how to keep your drives safe and compliant. Thanks for joining me today, Steve.
Glad to be here, Greg. Thanks for asking me to participate.
Do you want to give the listeners a little dive into your background?
Sure. My whole career has been in the drives business for 35 years, and I spent about 16 of that with Rockwell, but the beginning of my career was with a company called Magnatech that used to brand label the Yaskawa drives. And at some point in time, I reconnected with the guys that I used to know that then later became part of Yaskawa. And for the last 14 or so years, I've now been with Yaskawa, so my total Yaskawa time is sort of like about 19 when I add the front and the back together.
Fantastic. And for those that want to hear more about the Magnatech story, I'll give a little pitch for our episode called Back in My Day, where Mark Bernicke tells the entire backstory of how Magnatech became Yaskawa. As you can tell, Steve has a wealth of knowledge, so I'm excited to get into it. My first question for you, what is available fault current, and why is it important in the context of drive installations?
That's a good question, Greg. Well, available fault current is the maximum current that will flow at a specific location on a circuit under short circuit conditions. For example, when a branch circuit feeds an electrical panel or device, the amount of short circuit current available to that panel or device is what's referred to as available fault current. It's important because panels and devices are required to safely withstand the amount of fault current available at that location.
So if I'm understanding it, at any point in the circuit, if I take two wires and touch them together, straight out short circuit, that is how much current will flow. That is the SCCR, correct?
Yes, that's what would be the available fault current, what flows under a short circuit condition at a specific location.
So what are the risks if that available fault current isn't properly accounted for during installation?
Well, when a short circuit condition occurs within equipment, there's arc flash and violent explosions that occur. So if the equipment isn't rated high enough to safely withstand these conditions, there's risk to humans and possibly equipment, and it's significant.
I think we're all familiar that we need to size circuit breakers based on protecting what's downstream. This is kind of similar in that our device needs to be able to withstand whatever that available fault current is.
That's correct. You wouldn't want to have, for example, a circuit breaker that's only rated for 25,000 amps, but yet your available fault current is 100,000 amps. That would be a problem if a short circuit occurred. If the short circuit didn't occur, okay, you could say that no problem, but there's a risk.
Around this whole available fault current, what types of protection are typically built into a variable frequency drive?
So variable speed drives, variable frequency drives, they do have some protection, but not for what we're talking about here today. They protect themselves against many things, including things like momentary overload. So you're running at a certain percent load, and now you go to 150% load for 1 minute, that kind of a thing. They protect themselves against that. That's momentary overload protection. They also protect themselves against temperature because most drives have built-in temperature sensors. And they also protect themselves against excessive regeneration. So when a motor slows down or drive slows down, there's energy that comes back onto the bus, and a drive is going to protect itself against too much of that, which forces up the DC bus voltage. So it protects itself against that also. And even output short circuit conditions. So when we're talking about short circuit, there's really, if you look at a drive, the drive could either have an internal short circuit or somebody's doing something they shouldn't on the output of the drive, like shorting the motor wires on the output. Well, today's drives can react so quickly with their microprocessors and the way they control the power transistors that it actually can react fast enough to protect itself against somebody shorting the output of the drive. But what it can't do, it has no choice of doing, is if there's an internal short circuit, such as on the DC bus, right? There's
Yep.
nothing, there's no control there that could possibly interrupt what's going on an internal short circuit. And that's why we're talking about this today, is because all drives have that possibility of that happening, and they can't protect themselves against that.
Yeah, on the output side of a drive, you're essentially controlling switches. So the microprocessor turns all the transistors off or the switches off, and
Yep.
hopefully problem avoided.
Yep, it can react in milliseconds, if not microseconds.
And when you talk about a brief overload, you mentioned 150%. In the grand scheme of things, that's small. Often when we're talking available fault current, we're talking tens or hundreds of times what the rated amperage of the device is.
Correct. Overloads are a lot different from short circuits. Overloads is usually resulting from something mechanical. You've got something going on the machine that requires something for a short period of time in excess of the normal load. That's what overload is all about.
Yep, a few too
Yeah.
many people got on the escalator this morning.
Yeah,
No.
exactly. Right.
Since we need to be careful on that input side of the drive, is that why we would use something like an overcurrent protection device, an OCPD, even though the drive does have some built-in protection?
That's correct. So with few exceptions, most drives don't include that internal short circuit protection. There are a few that we will talk about, but most require supplemental protection, so fuses or breakers or something on the primary side of the drive for this specific failure mode. A rare exception to this is Yaskawa's matrix drive, which actually does have input fuses that are embedded within the drive. That's a rare exception. Most drives don't include that.
And for those of you that don't know, our matrix drive is our low harmonic and full regenerative drive offering. It's kind of cool that when they designed that, they built fusing into it. I've seen another term, and I know we're throwing a lot of terms and acronyms out there. This time it's AIC. So can you explain the difference between SCCR, which is short circuit current rating, and AIC, which is amps interrupting capacity?
Yeah, that is something that is often confused. Let's talk about SCCR, or short circuit current rating, first. Short circuit current rating is a rating given to a device that's capable of safely withstanding a maximum amount of fault current. Safely withstanding is the key word. That's what it does, is it safely withstands it.
Doesn't mean it survives it, it's just withstanding it.
Right. It safely withstands it.
Okay.
Right. Could be destroyed, but if it's destroyed but it was safe, it's okay.
It's not going to start a fire or hurt anybody,
Correct.
even if it is destructive.
Correct. For example, a drive that has a SCCR rating of 100 kA, 100,000 amps, means that it can be safely used on a circuit with an available fault current up to 100,000 amps. However, and this is important, since most drives don't include their own internal short circuit protection, customers have to use them in combination with approved protection devices to achieve the SCCR rating. And so if you see, for example, a label on a drive that says SCCR 100 kA, it's true, it can be used on a circuit up to that much of available fault current, but you have to follow the instructions, and the instructions say use it with fuses or use it with breaker, use it with this other device. Okay, that's when it truly meets it, but only up to 100,000 amps. So, for example, you couldn't take a fuse that was capable of 200,000 amps and use it on the input of a drive that's only rated for 100,000 amps, and now you think you have 200,000 amps capability. You don't. It's always the weakest device in the string.
Because if that fuse allows 200,000 amps through that drive, which will fail, may not fail safely in that case.
Right.
And that's what we're trying to avoid from the get-go. So that's
Right.
a great thing to point out. That is a drive, and this is probably for more than just drives, other automation equipment out there, if it has an SCCR rating, you need to check the manual to make sure that to achieve that, you don't need a supplemental device.
Right.
And when we talk about those supplemental devices, let's say it needs a circuit breaker. Can any circuit breaker work, or will each manufacturer have specifically tested models that need to be used?
Well, there's a few different types of circuit breakers. One is called a molded case circuit breaker, otherwise known as MCCB. And right now, the UL says if you test with an MCCB and you get a favorable result, that you can use anyone's MCCB.
Okay.
Now, there's other styles of circuit breakers like MCPs, motor circuit protectors. And those types of devices, if you test with it and you publish, this is the one that we tested with nothing else, then it has to be that specific one. So you do have to be careful about which style of circuit breaker you use. And most drive manufacturers, they show in their literature, in their user manuals, if there are specific restrictions on which devices can be used. Most drive manufacturers spell it out in their manuals.
Okay. Is that because the characteristics of how an MCP stops the current or opens the circuit, that they have to be unique compared to your MCCBs?
Yeah. MCPs are typically, but not always, magnetic trip only, whereas MCCBs are thermal and magnetic. So it has something to do with that. And that whole thing of why MCCBs can be considered generic and these other devices can't be considered generic, but that's a whole nother topic.
That's deeper than we want to dive in today's episode.
But to continue answering your questions, the takeaway on that short circuit thing is you have to pay attention to what's in the manufacturer's instructions. You just really have to. And that didn't used to be the case. It's really important now that just to pay attention, whereas 10, 15, 20 years ago, these rules weren't what they are now. Okay, so you didn't have to pay as much attention to it. Now you really have to. Okay, that's short circuit current rating. Next, I'd like to talk about amps interrupting capacity, unless you have more question on the SCCR.
Nope, go on.
Okay, so now this thing called interrupting capacity, it's expressed in these units AIC, which stands for amps interrupting capacity. So it's like a unit, right? It's like an inch or a volt or something like that. They're units.
Okay.
Right? And this AIC, these AIC units, they apply only to devices that are meant to interrupt. So a fuse is meant to interrupt. A circuit breaker is meant to interrupt. But a lot of other devices, a terminal block isn't meant to interrupt. So it wouldn't have an AIC rating.
A VFD isn't meant to interrupt.
Right. And drives and electrical panels have a withstand rating. We just got done talking about SCCR. So a drive, we know it has a withstand rating or an SCCR rating. A panel has a SCCR rating, a short circuit current rating. But the panel generally would not have a interrupting rating, even though it might have a breaker or a fuse inside of it. But the entire assembly, the whole panel, which is an assembly of parts, is only going to have an SCCR rating, a withstand rating. It has a device inside of it that's interrupting with its own rating, but the panel as a whole assembly only has an SCCR rating.
So it's kind of like where you're looking at the circuit. If I open that panel up, everything downstream of that circuit breaker needs to be in alignment with what it might allow for fault current. But once I close that up and the panel kind of becomes a singular entity, now it has an SCCR, not an AIC, and I have to make sure that my available current upstream
is no more than the SCCR rating. So if you have panels rated at 65,000 amps, you got to make sure where you land the wires on that panel, it can't provide more than 65,000 amps of fault current.
And I asked this question in preparation of our episode today. I said, you can always keep going upstream. So where does the buck stop? Where typically is your limiting point that you could have the absolute most fault current from?
So most buildings, especially if you're talking about in factories, et cetera, something where significant power is required. You're going to have a transformer. It could be outside the building or maybe inside the building, but let's take a typical case where you've got maybe medium voltage at 4160 coming to the input of a transformer, and you've got 480 volt on the output of the transformer feeding all the loads in the factory.
Yep.
So that transformer is going to have some impedance. It's going to have some finite amount. If you have a dead short at the output of that transformer, the 480-volt side of the transformer, you can only get so much current to flow because the transformer does have impedance.
Okay. So again,
If
that's
it had
gonna
zero
be-
impedance, it would be infinite, right?
Yes.
But everything, even on the primary side of that, the wires out on the power lines, everything has impedance. The more impedance you have, the lower your available fault current is.
And when we throw around something like 100K, 100,000 amps of fault current, is that easy to obtain, or would this secondary of a transformer not even be able to provide that much in most real-world situations?
I would say in most real-world situations, it's going to be difficult to get to 100,000 amps. Now, you could have some really large transformers that are low impedance where you could really have that kind of fault current right at the transformer. But it's rare. I've seen some applications where on a 1,000 horsepower application, you've only got 18,000 amps by the time you reach the load. Because remember, not only is there the transformer, but there's cables that have impedance. And you could be going hundreds or thousands of feet with those cables. So by the time you actually get to the load or to the panel, that your available fault current is probably, in many cases, often way less than what people specify.
Yeah, us engineers, we like to over-engineer stuff, so pretty safe to say that 100K rating is a fairly safe rating in most industrial situations or factories.
Right.
So Steve, can you tell me, I think we've touched on it a little, but what are the consequences of using equipment with an SCCR that is below the available fault current at the installation site?
Sure. Well, think about this. If there's an accidental short circuit, let me rephrase that. If an accidental short circuit never occurred, there wouldn't be any consequence. This is all about if you had a short circuit.
Yep.
So if you don't have a short
hopefully.
circuit, you could argue no harm, no foul. However, that would be risky. I think of it like driving a car without airbags and without insurance. You could do it, but do you want to? If that short circuit occurs, human injury and liability could be severe, but only if it occurs.
And it would be severe because the device can't handle that available fault current. Therefore, there's high potential for it to fail dangerously, right? We talked about how SCCR rating is, we want a device that may not survive the short circuit, but we want it to fail safely. So when you talk about this potential for danger, like crashing your car with no airbags, this device could explode, doors could fly off, arc flash could occur. If there's flammables nearby, a fire could start, things like that. That's our worst case scenario that we hope never happens.
And I think we've all seen arc flash occur in our life somewhere, right? There's sparks, there's plasma, there's explosive forces. So you know you're going to get some of that. It's just how bad is it?
I know at some point in my life I've crossed the wrench across the terminals on the 12-volt lawnmower battery, and that little guy sparks pretty good on his own. I wouldn't want to see that with a big 480-volt system or more.
Exactly.
So you touched on UL standards, and like all standards do over time, they change. But how have the standards for drives changed in recent years, particularly with the shift from UL 508C to UL 61800-5-1?
Well, just to make sure everybody's on the same page here, UL I think most people are familiar with, but it stands for Underwriters Laboratories, and it's a company whose purpose is to certify products to make sure they're safe for humans. Well, UL 508C, which has been around for quite a long time, is an electrothermal safety standard for power conversion equipment specifically. And it's evolved over the last few decades to be more stringent, which has resulted in new restrictions for installing and applying variable speed drives. So it's evolved. It didn't stay stagnant.
As we would expect with time and new technology comes out, you need new standards to keep everything safe.
Right, but it evolved even prior to the introduction of the new standard. So it's not like, well, here's the requirements for testing, and that's what they're going to be for 20 years. Even under 508C, the testing requirements change.
Right. There was evolution over time.
The evolution just of that standard. But then at some point in time, I'll say 508C was retired. and a new standard replaced it, and that's called UL 61800-5-1. It's the successor to UL 508C, and it includes even additional test requirements above and beyond 508C that became more stringent, right?
Yep.
And it's harmonized with the European equivalent by the same number. It has an IEC in front of it instead of UL. So IEC 61800-5-1. So if you see that, realize that the two are related, but they're not 100% equal.
That's good to know.
Okay. Now, UL 508C products are still valid for sale and installation, but manufacturers are no longer able to introduce new products under the old standard. So you can't develop a new product now and try to get it listed under UL 508C. They won't do it. They say, nope, you've got to do the work for the new standard, 61800-5-1.
I'm going to take a guess here. I'm going to call it 5-1 for short. But you already mentioned it's a little bit more stringent. So if you have an existing product that's certified under UL 508C, does it automatically meet the new standard, the 5-1, or does it need to be recertified?
Yeah, UL won't just say, hey, this was a 508C product, therefore it can be a 5-1 product. They won't do that. So we have to do the work, retest per the new standard. Now, that doesn't mean any changes to the product whatsoever. There could be cases where we decide to do something different, but usually not. The new products that are certified to 5-1 aren't necessarily any safer than the existing products that are 508C. It's just that we had to test them by the new method.
That makes sense. So with there being stringent electrical standards, and again for good reasons, for the protection of people, equipment, and so on, can you go a little deeper into why it's so critical for customers to follow manufacturer instructions when it comes to drive installation and protection?
That's a natural question, Greg. I would say it's because short-circuit protection requirements have become more restrictive. Because of that, it's important to understand and follow instructions to avoid the risk and liability, because it's sort of easy. If you don't follow it, it's easy to make some assumptions and make mistakes. And without paying attention to the detail, mistakes are likely to happen.
And I'm sure nobody wants to be responsible for injuring a coworker or themselves, or as we always say, if you come to work with 10 fingers, we want you to go home with 10 fingers. Right?
Exactly.
So aside from, we've been talking a lot about the electrical protection, but are there other instructions when it comes to installation around ventilation or volume or other details of a panel?
Another good question, Greg. So when looking at the variety of approved protection devices for drives, which you'd have to look in the instructions, right? It's the only place to find it. You may notice an array of solutions and conditions of use. So a drive manufacturer could say, oh, you can install the drive along with the fuse, or you can install it along with the circuit breaker, et cetera, et cetera. So there's this variety of solutions that a drive manufacturer may or may not provide to you. While some of these protective devices require that the drive be mounted in an enclosure of a minimum volume. And the reason is that relates to the size of the enclosure used during the short circuit test that a manufacturer performs. And when we do these tests, it's a destructive test. We purposely destroy the drive to see what it can handle with a fuse on its input or with a circuit breaker on its input, etc. So those conditions when we test it, if there's conditions where we tested it, hey, the drive was inside of another enclosure, the drive was outside of an enclosure with the NEMA 1 kit, all those kinds of things, however we tested it and got it to pass is how it must be used. And that's why you see things like minimum enclosure requirements for some of the protective devices.
That makes sense, because if it can withstand a current in one condition, but it's a lower amount of current in another, then that all needs to be documented and made sure that those instructions are adhered to.
Right. And if you don't pay attention to that and you install it in a way that it wasn't meant to be used, it would be a violation of UL. And that would be up to whoever who's creating a panel with a drive inside of it, or whoever's installing it or planning it. it would be up to that person to pay attention to make sure the right protective device is being used for the application.
You're bringing up a great segue to my next question, which is, at the end of the day, who holds responsibility for ensuring SCCR compliance? So I could be a panel builder or even a machine builder, and I install everything, but then I pass it on, I sell it to someone else who now owns it. At the end of the day, who is ultimately responsible that there is this SCCR compliance?
That's a good question. I'm not sure anybody knows the absolute answer to that, but here's what I believe is that the installer has a responsibility to check that properly rated equipment gets installed at the point of connection, because as you an installer, you don't just install things blindly. You would need, as an installer, to understand what that fault current is that's available where you're connecting it, and then what that panel or device is rated for. That should be a responsibility of the installer. That's my belief. Now, the specifier or planner has the responsibility to choose the properly rated equipment.
Yep.
Because otherwise the equipment could show up and it's the wrong thing. There's too much fault current for that panel that just arrived.
Yep.
Right?
Then the installer doesn't install it, and now
that's what should happen.
Now your project gets delayed 6 months.
Right.
Or you're forcing someone's hand to do something that they shouldn't be doing, like installing it anyway.
Yes.
That being said, we've all watched shows about lawyers, and you don't want to be any part of that chain of potential responsibility. So I'll say the onus falls on everyone you mentioned, from the designer to the installer, because the truth of the matter is, if somebody gets injured, unfortunately, and lawsuits come out of it, every single party along the way could be held accountable. So I'll just say it's really important, and everyone needs to be aware of what they're doing when it comes to this topic.
Agreed.
What should customers do if they don't know the available fault current at the point where their equipment is located or connected?
Yeah, we've certainly run into this in the past. And I would say, with the help of an electrical engineer, customers should at least determine the worst case available fault current at the output of their power source. Kind of like what we talked about before, where if you at least know the transformer impedance, the voltage, that kind of thing, it shouldn't be that difficult to at least determine what that fault current is way back at the source, even without your wiring or without additional line impedance. That should be worst case, but it does require a little bit of work. And then it'd be more beneficial to know enough information and run calculations with knowing the cable impedance, or if you've got another device that has impedance in series, like a reactor, right? That's going to knock down the fault current a lot too. So that's going to actually offer a better result. In other words, a lower available fault current, which is real because cable has impedance. The more information, the better. Some customers, unable to determine their fault current, specify equipment with 100,000 amps, like we talked about before.
Figuring there's no way that available is going to surpass
so that's
that.
Fairly safe. I won't say it's 100% safe, but it's fairly safe. Or they can also add line impedance, such as a reactor. Reactors have a fair amount of impedance, and that's really going to knock down the available fault current as well. But this can result in significant extra cost. Unnecessary too, right?
Yeah. And I do remember earlier in my career seeing facilities where, like about anything, you can do a paid study. So you can have an engineering firm come in, and I believe they were going through and figuring out available fault current and putting stickers on the different panels that kind of told you what it was throughout the facility. And while the study might cost money, the good thing is you don't have to over-engineer your panels then. You don't have to say, I need to have 100K everywhere. If I actually have the study done, it might cost me a little money, but now I know I only need to design a panel to 35K, for example.
Right.
And it actually saves me money in the long run on the equipment and other things necessary. So just throwing options out there, it kind of gets you thinking a little bit. But it is a great thing to know if you are a facility owner and are putting in new equipment. That really brings me to the end of my questions on the topic. I think we've done a great job without the aid of visual aids to talk through this. But if you had a couple key takeaways you wanted our listeners to go away from this episode remembering, what would they be?
Yeah, I would say the biggest things, Greg, would be for customers to understand or try to understand, calculate, determine what their available fault current is, where they want to connect a load, and then make sure that you choose equipment with an SCCR or a withstand rating that's equal to or better than the available fault current. That's a key thing to remember. And then in addition to that, when choosing equipment, individual components, understand and follow the detailed instructions for approved protection devices and conditions of use. So the devil's in the detail a little bit.
As it often is with engineering.
Yeah, and unfortunately, you could argue it's safer now than it's ever been, but it's also a little more complicated than it's ever been.
And I'll add one more to your list. Your final SCCR of, say, a panel is always equal to the weakest link. So when you are picking out those components, you need to match the level of the entire system or the level you're trying to achieve.
Right. Yep. If you've got a 65 kA circuit breaker in there, but some other device inside of the panel is only 10 kA, your panel, unless it's been combination tested, it can only be rated 10 kA, even though you got a 65 kA circuit breaker in there.
Great. Anything else?
No, I don't think so, Greg. Great topic. Thanks for the opportunity.
Absolutely. That's going to wrap up today's episode on drive, short circuit protection, and UL standards. From understanding available fault current to navigating UL 508C and IEC 61800-5-1, we hope this gave you a clearer picture of how to keep your system safe, compliant, and future ready. A big thank you to Steve Pearl for sharing his insights and expertise. Steve talked about the illustrious career he's had, and by the time this episode airs, Steve is actually going to be on to the next chapter of his life, enjoying retirement. So from all of us at Yaskawa, I'd like to give you a big thanks. You've been a big mentor in my couple of years here now, and I know you've done a lot of great things in the drive industry throughout your entire career, and you will be greatly missed.
Thanks, Greg. Yep, it's been a great career. I enjoyed working with everyone at Yaskawa and other places, and I learned a lot over the years, and I'm also happy to share my knowledge, so thank you.
If you want to learn more about the topic we discussed today, Steve actually has a recorded webinar. I'm going to put a link in the description of this episode, and as always, you can reach out to your local Yaskawa sales engineer or distributor. We're always here to help. If you enjoyed today's episode, please like or follow this podcast to stay informed of when new episodes launch. And if we're doing a great job, please leave us a 5-star review. Thanks for joining us, and as always, we'll see you next time on VFD Vibes.